Welcome to Session 15, Exponential Models and Geometric Sequences. This lesson develops mathematical reasoning that stays reliable when a problem looks unfamiliar. You will learn to distinguish additive from multiplicative change, to model growth and decay, and to index geometric sequences. These are connected habits, not isolated tricks. Keep a pencil ready. We will build a mental model, use a repeatable method, solve a demanding example, diagnose an error, and finish with an independent checkpoint. Start with this principle. Exponential change repeats multiplication by one factor. Uses visual structure. A equals A0, B to the power TAN equals A, 1, R to the power N minus 1. Read every symbol and label before calculating. The first goal is to distinguish additive from multiplicative change. Connect it to the second goal, model growth and decay. Correct calculation begins with correct interpretation. When the surface details change, search for the same relationship underneath. Transfer means choosing the structure from evidence rather than waiting for a familiar-looking example. Step 1. Check consecutive differences and ratios. State the target and preserve its units or conditions. Step 2. Identify the initial value. Use a separate line so signs, factors, and labels remain visible. Step 3. Convert the percent to a factor. Keep the reasoning efficient, but never skip an operation that could hide an error. Step 4. Count the number of multiplication intervals. Verification is part of the solution because it tests the answer from another direction. Signal 1 is constant difference. Respond by remembering. Use a linear model. Name the response before calculating. Signal 2 is constant ratio. In that case, use an exponential model. The form tells you which tool fits. Signal 3 is term n in a geometric sequence. Remember, use exponent n minus 1. This separates plausible work from valid reasoning. If you cannot name the signal, pause and classify. A deliberate choice of method is usually faster than repairing a rushed setup. Here's the challenge. A population starts at 800 and grows 5% yearly. Which model is correct? Restate what is requested before touching the choices. The first move is check consecutive differences and ratios. Apply it directly to the quantities and conditions in this problem. Now use the core reasoning. The initial value multiplies by 1.05 each year. Keep each equality, comparison, or unit conversion visible. Pause for a midpoint audit. Check copied values, signs, units, restrictions, and whether the current result is the requested quantity or only an intermediate value. Continue by applying this control. Convert the percent to a factor. The explanation supports one option without relying on its position. The mathematical conclusion is 801.05 to the power t. State it with any required units, interval notation, or restrictions. The final answer is 801.05 to the power t. Compare it with the exact target and reject any choice that represents a common intermediate step. Verify from another direction. Compare the model with two known terms or time points. The check should use evidence independent of the original calculation whenever possible. Try this checkpoint without copying the example. An exponential model doubles every 4 hours. How many doubling intervals occur in 18 hours? Decide which mathematical fact controls the answer. Pause and write one line of reasoning before committing. A visible decision is easier to inspect, explain, and correct than an unsupported guess. First hint. Divide elapsed time by 4. A continuous exponential model permits 4.5 intervals. Use the hint to repair the setup, then finish the reasoning yourself. The accepted answer is 4.5. Explain why it works, and name the earliest line that would reveal a likely error. The central message is to distinguish additive from multiplicative change. Combine that with the discipline to model growth and decay. Finish by remembering to index geometric sequences. A result becomes dependable only when the method and verification are both clear. Reflection. How many actual growth intervals occur before the requested term? Name the exact point where an incorrect path would first become visible. Practice one fresh problem for 8 to 12 focused minutes. Keep the work readable, verify independently, and carry the routine into the next session. Before moving on, close the notes and explain the method aloud from memory. Then invent one small variation, predict how the answer should change, and verify that prediction with a complete calculation.